We are Group 5 and going to present the final result for the course project. The category topic we choose is the Allo Merchant category recommendation. Here is the outline that we will cover in this presentation. First is the introduction of the problem. We are tasked to develop algorithms to identify and serve the most relevant opportunity to individuals and to improve customers' lives and help Allo reduce unwanted campaigns. Here is the evaluation score using this project, which is based on root mean square error between the predicted value and the ground truth value. The lower the RMSE, the better the model's performance. Next part is the exploratory data analysis. We performed various analyses to find out the inherent characteristics of some feature, their relationships, and finally get some idea to help us perform the following tasks. First, let's look at 5 datasets. Train set and test set contain card ID and information about the card itself, and so on. The train also contains the target, which is the loyalty score. Historical transaction set contains up to 3 months of historical transaction for each card ID. Merchant set includes additional information about all merchants in the dataset. New merchant transaction set contains 2 months of data for each card ID, containing all purchases that each card ID made at a merchant ID. The following figure illustrates the percentage of missing value for the feature in different CSV files. There are a total of 6 variables that contain missing values. Features with missing value can negatively affect the machine learning code. Thus, the imputation is required. From the following figure, we can see that some of the loyalty values are far apart compared to others. These are almost 1% of the data which target lower than -30, which seems to be a special case. Since these rows might play an important role in the learning, we will perform further analysis on this data to uncover whether they should be included or excluded. In addition, we try to analyze the distribution of the first active month of the card in train set with respect to the number of cards. We also confirm that the shape of the distribution of first active month is similar to that of the test set. Therefore, a model that is considered to include the first active month feature can help to predict the target. Next, we try to find the possible relationships between target and 3 feature variables in the trained dataset. From 3 figures, we can see the distribution of different categories in all 3 features is similar. As a result, we cannot simply find the direct relationships between features and target. We decide to perform feature engineering on several columns that may affect the prediction of the target. In summary, we can conclude several ideas from the data analysis. Firstly, target variables are real numbers. It directly gives us the intuition that we have to go for a supervised machine learning regression model to solve this problem. The dimension of train and test data is very less. That clearly shows that the information provided is not sufficient for training. More features must be added to this with the help of domain knowledge and the business problems given. Thirdly, the target variable is normally distributed, but there are outliers which seems to be accumulated around -30. Data is not complete as missing values are presented in the merchant, historical and the new merchant transaction. So these missing values must be imputed for better prediction. Finally, the type features can reveal the inherent property of the transactions, and the transactions are time dependent. The engineered features from the features like first active month will be useful in the prediction.
Next part is data preparation and preprocessing. Firstly, we need to clean the datasets provided. First, we need to encode the categorical features. The categorical features except edit features in transaction sites include authorized flags, category 1 and category 3. We simply map each class into a corresponding representative integer with dictionaries. Next step is datetime parsing. There are some variables like first active month in train set and type set, and purchase date in transaction sites that should be primarily parsed as datetime type data. Next data preprocessing step is feature engineering. First, we expand the datetime feature. We try to extract more features from the datetime type variables like the specific day of week, week of year, month, year, day, hour, and so on. Additionally, we also try to create some new features with the current daytime related features, like purchase day since active day and purchase day since reference day. Next, we have created aggregations over the features. We calculated the aggregation of the numerical variables, which may include all or some from mean, minimum, maximum, variance, sum, screw, and other aggregates. We also created some behavioral features. In order to mine more information from time and user behavior information, we focus further on the transactions datasets. Here, we considered constructing some features used to describe user behavior activities, including the difference between the last transaction and the first transaction of one card ID, the difference between the card activation date and the first day to purchase, and so on. Finally, we created some more features using simply adding, multiplying, and dividing operations. For example, we had feature sum, which is the sum of feature 1, feature 2, and feature 3. Next is missing value imputation. We simply replace the one missing first active mask in the typeset with the earliest mask of all purchase dates. For the missing categorical values, we replace the null values with the mode of that column. Then we will give further explanation on the machine learning model approaches we used in this project. The first approach that we used is artificial neural network. We created a 4-layer network with one input layer, 2 hidden layers, and one outer layer. We use the ReLU activation function in the hidden layers. A fetch norm layer is added after the hidden layer, followed by a drop-off with drop-off rate equal to 0.7. The final upper layer is a dense layer with linear activation function. The loss is defined as mean square error. The batch normalization layer is used to normalize the values across each column so that the values of the column has 0 mean and 1 variance. It helps speed up the training by allowing higher learning rates than faster convergence. To avoid overfitting, we use dropout and early stopping methods. Dropout randomly drops neurons from the networks during training, thereby reducing the overfitting. Early stopping stops training of the network when the validation error starts to increase, which indicates overfitting starts to occur.
For the second approach of our machine learning models used for our project, we use the random forest model. A random forest is a meta-estimator that fits a number of classifying decision trees on various subsamples of the dataset and uses averaging to improve the predictive accuracy and control over fitting. The model first starts by growing multiple decision trees which are then merged together to obtain a more accurate prediction. The motivation behind using the random forest model is that multiple uncorrelated models, which are the individual decision trees, perform much better as a group than they do alone. The next approach we have is the light GBM model. Light GBM, short for Light Gradient Boosting Machine, is a gradient boosting framework that uses tree-based learning algorithms. Along with other decision tree-based methods, Light GBM can be used for both classification and regression problems. Light GBM splits the tree leaf-wise as opposed to other boosting algorithms that grow the tree level-wise, which means that given a condition, only a single leaf is split depending on the gain. Since the leaf is fixed, the leaf-wise algorithm has lower loss compared to the level-wise algorithm. One other characteristic of Light GBM is exclusive feature bundling, in which the algorithm combines exclusive features to reduce dimensionality, making it faster and more efficient. Light GBM also happens to be our best performing model with the lowest RMSE score obtained. For approach 4, we have the XGBoost model. XGBoost, which stands for Extreme Gradient Boosting, is a scalable distributed gradient boosted decision tree machine learning library. It provides parallel tree boosting and is the leading machine learning library for regression classification and ranking problems. This extreme gradient boosting involves building a model consisting of multiple decision trees. It usually improves a model by combining it with other weak models to generate a strong one. Before the next model is generated, gradient boosting sets targeted outcomes for the next model in an effort to minimize errors based on the gradient of error. Next, I'll talk about the CatBoost model. CatBoost is an open-source gradient boosting algorithm. Its name comes from the two words category and boosting. CatBoost has been applied to many areas such as recommendation systems, self-driving cars, forecasting, and virtual assistants. CatBoost uses gradient boosting, which is a part of ensemble learning. It combines the predictions from many weaker models to get more accurate results. In short, the CatBoost model is developed through training a data set, which is a set of objects with known features. Accuracy is then checked on the validation dataset. During training, decision trees are built continuously. Each tree is built with reduced loss compared to the previous trees. We have tuned hyperparameters for the model, such as depth, learning rate, as well as mean data and leaf. This is done through k-fold cross-validation.
Next, we will move on to the remaining models and solution novelty. Simply put, voting combines the predictions from different models to deliver a more reliable result, which is the mean for the three boosting algorithms. For the last solution, the boosting models are stacked using the Bayesian regressor. The stacked models are then averaged based on their marginal posterior probability. As noticed in the exploratory data analysis, there is a group of outliers in the target lying around -30. Therefore, besides training regressor models, we also train classifier models to predict whether a card ID will belong to outliers. For each boosting algorithm, we train 3 models, which are simple regressor model over all data, regressor model over normal data, and classifier model for outliers. Correspondingly, we had 3 types of prediction results after stacking the 3 models. We finally get the prediction from the equation as shown in the slides, where prediction's binary stack is 1 for outliers and 0 for normal data. This means that if a card ID is predicted to be an outlier, its loyalty score will be -33.2. This is the mean score for outliers in the train set. After performing stacking with outlier predictions, we get a final ranking of 505. We can see the prediction for outliers has significantly reduced the RMSE as compared to other models such as XGBoost and CatBoost, which are 2000 plus ranking positions. It also aligns with our prediction that outliers have significant impacts on model results. Next, we will provide an overview of the results from different models tested. As we can see from the leaderboard, LightGBM performs the best with the lowest RMSE score of 3.68426. It also has the highest ranking position of 361, which places us at the top 8.78%. Next, we will summarize the key learning points from this project. Throughout this project, we knew the importance of exploratory data analysis and preparation. When carrying out data analysis and preparations, we realized that there were many features with missing information and potential anomalies. To tackle such issues, we performed data cleaning, missing data imputation, and feature engineering. Hyperparameters define the fundamental construct of a model. It is rare that a model will perform at the perfect level just in the first instance. Hence, multiple cycles of adjustments are needed during the training process. In this project, we explored some ways to tune the hyperparameters, including grid search, where grids are made up of hyperparameters and different values. Each possible combination is then tested. However, this is very inefficient in terms of training time and cost, hence we did not take up this idea. Instead, we approached the k-fold cross-validation method, where data is split into test set and k number of folds. The cross-validation then iterates through the folds, and at each iteration uses one of the k folds as the validation set. By testing and training the model k number of times on different subsets, we get a more accurate representation of hyperparameter values. This method is also much less time-consuming on our PCs. Finally, I will conclude our project with a short summary. We started off with exploratory data analysis and pre-processing. These are important steps as they can provide us with context on how some features relate to others. At the same time, we have cleaned and prepared the dataset by handling missing values. We also performed feature engineering by creating new features. These build a strong foundation for the upcoming model building and training. In this project, our team has utilized a total of 8 models. The hyperparameters of the models were tuned during training. From our analysis and findings, we have found LightGBM to be the best performing model. In conclusion, through this project, our team has gained a deeper understanding of machine learning in real life. These experiences will give us a greater insight in the future related applications.